All right, guys, we're going to have two videos. We're going to cover ethers, epoxides, thiols, and sulfides. We're going to cover nomenclature on all of them, and then a few prep and additional reactions for ethers and epoxides. So let's go ahead and get started with our ethers. So ethers specifically are ROR, but that you have to be careful. Just because it's a carbon doesn't mean it's an ether. If it's a carbonyl, we're now in ester or anhydride territory. It's got to just be a carbon right here attached to other carbons or hydrogen. They're found in a lot of different natural and synthetic products. It's a pretty common functional group. And there's two different ways to name them. So when we get into nomenclature of ethers, there is sort of, let's say there's the common way and then the IUPAC way. It is important to know the common way because it is how a lot of simple ethers are named. And it's really easy. So it really takes the form of alkyl, ether. This works if the R groups are relatively simple. All right, you have ethyl, methyl, ether, and you just write them down alphabetically. Here you have a T-butyl group and a methyl, so you have tert-butyl methyl ether. If you have two R groups that are the same, for instance, this little guy, very, very popular solvent. This is diethyl ether. So there's no reason to write down ethyl twice. It's the same rules apply here with the Greek prefixes. And this guy right here, if you ever hear somebody refer to a chemical as just ether, this is probably what they're talking about. Has a history being used as an anesthetic. It's very, very common solvent in synthesis. And then you can see the limitations of that if you have more complex if you have more complex R groups. Ethers are actually very low on the priority list. So if you're not using the common name, the IUPAC name, it does not actually change the parent. You're always going to treat the ether as a substituent. So you're going to choose the more complex side to be the parent. So for instance, if we have, right, just some simple R groups here, you're going to choose the longer side. So you could call this butyl pentyl ether. But if you're doing the IUPAC nomenclature, you're going to pick the longer chain. This is the only substituent, so it makes most sense to name it to give the ether the lowest numbering possible. So this is a pentane, and on carbon 1, it's going to be based on alkoxy. So since there's 4 carbons here, it's butane, but we get butoxy. 1-butoxy pentane. You see that over here. This is a 2-carbon group, so it's based on ethane or ethyl. You get ethoxy. 1 carbon would be methoxy. Let's see. If we had, I just want to do one more example here. You often see them as little substituents, right? If we had something like this, maybe we'll do a methyl here, and let's do this. Okay, so we have a methyl group, an ethoxy group, and a methoxy group. So we're going to number to give the lowest numbering possible. So we're going to go 1, 2, 3, 4, 5, 6 on our cyclohexane. And then we're going to write things down alphabetically. So we have a 4-ethoxy. 2, methoxy is going to come before methyl, just alphabetically. 1-methoxy, 2-methyl, right, because O would come before Y, and then cyclohexane. Not really hard to name, but you should certainly practice naming, as we continue on and we add more and more pieces, it's a lot to manage. So make sure you're practicing. As far as structure and properties of ethers go, it's not very surprising. They tend to have very similar structures to alcohols in terms of the geometry, right? They can hydrogen bond with water and alcohols, but not with themselves. So they're considerably less polar than an alcohol, but they still are often miscible because they can participate in hydrogen bonds. They are a polar compound, so they have a higher boiling point than something like ethane that only has London forces, but considerably lower than something that can hydrogen bond with itself. It is also affected in terms of size, just like anything else. More London forces are going to mean effects in physical properties. Ethers are great for solvents because they are not particularly reactive, and because they are both polar and aprotic, they can dissolve a lot of variable compounds. And they're relatively low boiling, which is nice because that makes them easy to remove. Crown ethers are something that we're going... I don't know why they bring this up here yet. Crown ethers can also complex with metals, so you get this intermolecular force between a polar compound and an ion or a very, very strong partial positive. So you get this metal lone pair interaction, and it's one of the reasons why ether is such a great solvent for Grignards. It doesn't kill the Grignard like water would do, but it does stabilize it by forming these strong intermolecular interactions. There we go. There's a crown ether. So a crown ether is a very particular cyclic ether, and it's always an oxygen bound to another oxygen with two CH2 groups. And so however many oxygens you have and however many R groups you have, that's how you're going to name it. So first you're going to just count all of the atoms in the ring, so not the hydrogens, but the ones in the ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 atoms, and then crown, and then the number of oxygens, right? So 15, crown, 5. These are really interesting. You've got all of this electron density right at the center of the ring, right? You can see that here in this electrostatic potential map. And it can attract a cation, and it's just this perfect scenario where a cation of a certain size would get trapped in there, which can be really useful for solubility purposes. The different crown ethers have a different pocket size. So for instance, 18 crown 6 is perfect for potassium. Okay, that just says the same thing. So it helps you to dissolve salts that would normally not dissolve in nonpolar solvents. For instance, like KF. Potassium fluoride is very insoluble in organic solvents, but when you put a crown ether in, it gives all of this attention to that cation, and it allows it to dissolve better in something as nonpolar as benzene. So if you need a fluoride ion, a lot of times you're going to be working with crown ethers. And the different ethers are all perfectly sized for different cations, right? If you wanted to solvate lithium or sodium, you would just use one of the smaller crown ethers. You should know how to name them. All right, now preparation of ethers. There's going to be some new, some review, some combination. All right, we're not going to focus on this industrial reaction. It's great industrially, and it's good for very simple symmetrical ethers. We're going to be more interested in reactions we have a little bit more control over. And so Williamson ether synthesis, and I'm actually going to start on the next page here. This is definitely a reaction and mechanism that you should know. And this is a great way to make an ether. And frankly, it's not even that new of a reaction. You've done the second part already. So the first part is deprotonation. So you're going to start with an alcohol, and you are going to use a really strong base. NaH is what I would recommend. That's what you're most likely going to see in practice problems and problems from me. And then in the second step, it's just an SN2 reaction. So once you deprotonate, it would be like putting an alkoxide with an alkyl halide, which is just a standard chapter 7 SN2 type reaction. So you wind up getting your ether. Yes, your ether. So in the mechanism, really simple here. Your base, in this case, it's a hydride, so looks like that, or you could just write NaH, is going to pick up this proton, leave the electrons with the oxygen, and you get an alkoxide. When you add in Rx, right, just SN2 reaction, assuming that's not a tertiary alkyl halide, and voila, we have our ether. Very, very simple reaction. This is one of the main ways that you guys are going to make ethers. You see you've got some notes on the mechanism here. You want to be thoughtful. If you were trying to make something like this, it could be difficult because you do want an SN2 reaction to occur, and you know SN2 isn't going to happen there on a tertiary alkyl halide. So you would want to start here. This one would be difficult to make, except for CH3 can't be eliminated. So you actually do get tert butoxide acting as a nucleophile for the first time rather than a base. I will not try to trick you. Don't worry. Just know, as with any reaction, there are often practical considerations. Now, this is another one that is a little bit new and a little bit old. This is alkoxymercuration demercuration. So you know this reaction already, and you do need to be able to predict products with proper regiochemistry, but you do not need to know the mechanism. You already know oxymercuration demercuration that adds water across a double bond using mercury acetate and water followed by sodium borohydride. But if you switch it up and you use mercury acetate and an alcohol instead of water, you will get an ether instead of an alcohol. And it will be Markovnikov, and there will be no rearrangements. Let's see. We'll go here, and we're going to get an OR group and an H. All right, so this is another quick and easy way, at least maybe not quick and easy, but not particularly new way to make an ether. All right. So when you see this reaction, especially as we move into the final where all reactions are fair game, it's really important that you pay attention to what solvent is on that arrow with HgOAC2. It is going to make a difference in what product you predict. Now, as far as reactions with ethers go, there's not very many. And it's one of the reasons why they're such great solvents. They're good protecting groups as well because they're not super reactive. But it can undergo this one reaction, acid promoted cleavage. So you can kind of tear them apart. Essentially, what you're going to do, let's say that you have ROR. If you treat it with HX, you are going to get 2 alkyl halides. Now, it may be the same alkyl halide. It may be 2 different ones. It depends on if you're dealing with a symmetric ether or not. let's go through the mechanism. The first thing that's going to happen is your ether is going to get protonated, right? It's not that there's any good leaving group. There's no really good nucleophilic site or electrophilic site. So the first thing that happens is a protonation. And now suddenly we kind of have this good leaving group here. And we've got a good nucleophile with our X minus. It's going to attack one side. And it's going to pop off that alcohol. So we lose our first RX. Then we're left with this alcohol. Now this is a reaction, again, that you already know. If you treat an alcohol with HX, you can get a substitution. Because first we make the alcohol into water now, which would give us a great leaving group. And then another molecule or another halide ion can come in and kick that guy off, thus making our second RX molecule. All right, so acid-promoted cleavage is a pretty easy reaction. The mechanism is a few steps, but a lot of it is really building off of things we've already learned. This works well with HBr and HI. Don't worry too much about that. Again, I'm not going to try to trick you here. Since it is an SN2 reaction, it won't occur if we're on either a tertiary carbon. It'll go by SN1. If it's on an sp2 carbon, it won't happen at all. I won't give you that kind of an example. We are going to skip auto-oxidation, so you can skip from slide 24, 25, 26. You're not responsible for auto-oxidation. Now, in the next video, in the last video, we will address epoxides and then naming thiols and sulfides.